Before we start dealing with this particular praxis quiz, I think it would be a good idea to investigate the idea of standpipes in detail. What exactly is a standpipe for? Like, why would we install a vertical pipe here attached to the pipe with fluid flowing through it? What's the use of that?
To measure the pressure inside the pipe, because I think the difference in height between the point where the pressures are equal and what's actually inside the pipe is negligible usually.
Yeah, really the whole point of a standpipe like this is to effectively measure the pressure. For example, if we have, let's say we focus on just a standpipe itself. In fact, let me just zoom in on one of these. Let's say you have just standpipe B here. Let's say you've got fluid flowing through the main pipe. Fluid flowing through the main pipe here. And as a result of that fluid, you find that the water level in the standpipe rises up to a certain level, to a certain point. Let's say up to maybe 5 tick marks here. Let's say for simplicity that each of these tick marks is 1 centimeter. Doesn't necessarily have to be, but some sort of distance measurement. What would be, if we wanted to set up a Bernoulli equation, what would be 2 useful locations to compare within this standpipe, ignoring everything else around it? Because remember, the Bernoulli equation is all about comparing 2 points. What would be 2 points in this standpipe that would be useful to compare? Yeah, let's say this point where it's open to the atmosphere and the location at the bottom. Let's call that, let's just say top and, let's just say top and 0.2, since it's already labeled 2. So if we compare the location at the top and the location at the bottom, location 2, is there anything we know for sure about either one of those points? They have to have the same pressure? What do we know about the pressure at the top? Yeah, at the top, the pressure is 1 atmosphere, or atmospheric pressure, whatever we're calling that. And there's actually 2 ways we can describe that. The pressure at the top is the same as the pressure of the atmosphere. That much we know for sure. The pressure of the atmosphere we can describe in a couple of different ways. Have you seen the idea of gauge pressure versus absolute pressure yet? Then maybe we'll get to that later. But for now, let's just say that at the top, the pressure is the same as the pressure of the atmosphere, which is, yes, about 100,000 pascals. And do we know anything about the pressure at the bottom of the standpipe? That one's not really known, right? I mean, we might be able to relate it to pressure 1 or pressure 3 based on writing Bernoulli equations within it. Yeah, presumably it is going to be a higher pressure than pressure at the top. Because if we're comparing top and bottom, as you move down, what type of energy density is changing? Yeah, as you go from top to bottom, you're moving downwards. Your height is decreasing, so you're losing potential energy density. So from top to bottom, we have a decrease in potential energy density. What else is presumably happening to balance that decrease? Yeah, presumably this is balanced by an increase in pressure. From top to bottom, we're losing potential energy density and presumably gaining pressure to correspond to that. To be absolutely certain, we can write out the Bernoulli equation. If we start with the whole thing, and I would generally recommend starting with the whole thing, like so. But then ignoring stuff that's not actually changing. Is there any term in the Bernoulli equation that we know we can ignore when we're comparing points within this standpipe? Yeah, we don't need to worry about kinetic energy because nothing's moving. No motion means the speed at the top is zero, speed at the bottom is zero. There's stuff flowing within the flow pipe, the horizontal pipe at the bottom, but within the standpipe itself, there's no motion, so we can ignore speed. And yet there's no pump. There's current flowing through the flow pipe, but is there current flowing in the standpipe itself? No, the whole point of the standpipe is that the water in the standpipe just stays there. When you first set up the system, you are going to see water rising up into the standpipe, but it's going to reach some equilibrium level and then just stay there. So once it's reached equilibrium, the water in the standpipe stays in the standpipe. There's no further motion within the standpipe, so we don't have any current. So all that's left, the entire Bernoulli equation just becomes delta pressure plus rho g delta y equals 0. And this is where we see the idea that from top to bottom, we're losing height and therefore gaining pressure. We can even solve for the difference in pressure. If we think of this as, let's say we treat this as, let's say bottom minus top, P2 minus P top, plus density times gravity times height at the bottom minus height at the top. And those have to add up to 0. And let's set up a coordinate system here. Let's say we've got heights, and it would probably be useful to just call the height at the bottom height 0. So at the bottom, we'll call this y equals 0. And at the top, we'll call this y equals, it's the height of the water in column in standpipe 2. So let's say h2. Note that that doesn't mean the height of point 2, which we're calling 0. It's the height of the water in column 2. So we'll call that height at the bottom is 0, height at the top is h2. And what are we actually trying to solve for here? What's our goal in this Bernoulli equation? What are we trying to figure out? Yeah, pressure 2 is presumably the unknown we're seeking here. And to solve for P2, if we've got pressure 2 minus, and pressure at the top is just pressure of the atmosphere, rho times g times negative h2 would just be minus rho times g times h2. So there's our simplified Bernoulli equation. And then to solve for pressure 2, what do we need to do? How would we isolate pressure 2 here? Yeah, add these other terms to both sides. So we get pressure 2 equals rho times gravity times height 2 plus atmospheric pressure. So that's the pressure at the bottom. The pressure at the bottom is pressure of the atmosphere plus this extra rho g times height term, which means the more water is stacked above it, the higher the pressure at the bottom is. Any questions on the algebra of the Bernoulli equation so far there? And we could apply this to any standpipe. There's nothing special about this one particular standpipe. The same logic should work for pipe 1, pipe 2, pipe 3. So presumably each one of these other standpipes has a certain water level in it. And I don't know what they're going to be, but some sort of water level, whatever the water level it happens to be, we can say, and we can investigate that later, but we can say pressure 1 is rho GH1 plus pressure of the atmosphere. Pressure at location 2 at the bottom of the standpipe is rho GH2 plus pressure of the atmosphere. Pressure at location 3 is rho GH3 plus pressure of the atmosphere. So these are all going to be very standardized, very, very predictable. And this is why we say the standpipe effectively acts as a pressure gauge. The purpose of this standpipe is you can measure how high the water rises in it with a ruler, and then use that to calculate the pressure at the bottom. So you can sort of indirectly think of height in the standpipe as an indirect indicator of the pressure at the bottom of the standpipe. Any questions on that so far? Also, what shows up in every single one of these expressions for pressure? If you take a look at the formulas we just got for pressure 1, pressure 2, pressure 3, what do they all have in them? Yeah, they've all got this plus pressure of the atmosphere. So when you're making these calculations, like let's say you measure the height, you multiply it by density times gravity, and then you have to add 1 atmosphere. You take this height, multiply by density and gravity, and then add the atmosphere. Take this height, multiply by density and gravity, and then add the atmosphere, 101 kilopascals. The thing is, though, usually we don't really care about pressure. If we're comparing two locations, like let's say comparing points 1 and 2, in the Bernoulli equation, what we really care about is the difference in pressure. And if you're subtracting the pressures, delta pressure, let's say P2 minus P1, if you actually write that out, you're going to have rho GH2 plus 1 atmosphere minus rho GH1 plus 1 atmosphere. What's going to happen when you subtract those? Which part equals 0? What cancels out here? Yeah, the plus 1 atmosphere and plus 1 atmosphere cancel out when we're subtracting, which means ultimately the plus pressure of the atmosphere doesn't really matter. We just get rho GH2 minus rho GH1. So if you're talking about a delta pressure, you can basically just ignore the plus pressure of the atmosphere. What's left, the rho GH2 and the rho GH1, are what's often called the gauge pressure. The idea is that if the rho GH2 or rho GH1 plus P atmosphere, that is plus 101 kilopascals, is the absolute pressure. Absolute in the sense of this is what the pressure actually is. But if we ignore the pressure of the atmosphere, if we just look at the rho GH2, what we're essentially doing is we're looking at not the actual pressure, but instead how much more pressure there is than the atmosphere. So if you just take this pressure gauge, this standpipe, measure how many centimeters of water you've got, and multiply by rho g, you get a quantity that's called the gauge pressure. And gauge pressure is just describing your pressure relative to some reference point. Which is going to be atmospheric pressure. So for instance, if we say the gauge pressure is 50 pascals, that doesn't mean the pressure is actually 50 pascals. It means 50 pascals above and beyond atmospheric pressure. And the reason this is useful is that's what the pressure, I mean, the reason we call it gauge pressure in the first place is because that's what the pressure gauge tells you. For example, let's say we actually run the calculations here. Suppose we are dealing with this standpipe and we measure it, and let's say each one of these marks is a centimeter. So let's say this is 5 centimeters. In that case, we can calculate the pressure by taking density times gravity times H2. And what's density of water? Yeah, water has a density of 1,000 kilograms per cubic meter. Standardized because that's what the metric system was defined with in the first place. And Earth's gravity is what? What's the value of G on Earth? Yeah, closer to 9.8, but we'll round that off to about 10 meters per second squared. So multiply those and we get 10,000 kilograms per meter squared times seconds squared, since one of the meters cancels out. But then we're also going to multiply that by the height, 5 centimeters. Or more generally, let's say X centimeters. So density times gravity times height is going to be 10,000 kilograms per meter squared second squared times, let's say, X centimeters. In this case, 5 centimeters. For centimeters, though, that's going to be equivalent to what in terms of meters? What does centi mean? Yeah, centi, well, centi is 1 over 100, because 1 centimeter is 1/100th of a meter. So let's say X times 1/100th of a meter. That reduces the 10,000. 10,000 divided by 100 would just be 100. So 10,000 divided by 100, so we get X times 100 kilograms, and then one of the meters cancels out, so kilograms per meter second squared. And kilograms per meter second squared happens to be the same as pascals. So we can say density times gravity times height is X times 100 pascals. X being measured in centimeters. In this case, we've got 5 centimeters. So we get pressure to, that is density times gravity times height, is 5 times 100, so 500 pascals. In other words, you can take the height of water in centimeters and multiply by 100. That'll tell you density times gravity times height in pascals. Does that mean the actual pressure at 2 is 500 pascals? Would we say that location 2 has a pressure of 500 pascals? Because it's under 5 centimeters of water. Yeah, 500 pascals plus the atmospheric pressure. So if we want to find the actual absolute pressure at location 2, we would say location 2 has a pressure of 500 pascals plus 1 atmosphere. But if we just want to describe the gauge pressure, we would say location 2 has a gauge pressure of 500 pascals. in the sense that if you mark each centimeter as 100 pascals, like if you actually mark these, let's say 100 pascals, 200 pascals, if you just mark each of these rules on the cylinder, because each extra centimeter you go is another 100 pascals. So if you mark each of these centimeter marks as 100 pascals, you could say, oh, the water level is up to the 500 pascal mark. So we would say the gauge pressure at location 2 is 500 pascals. But 500 pascals of gauge pressure just means 500 pascals above and beyond the reference point, which is atmospheric pressure. So we'd say that at location 2, the gauge pressure is 500 pascals. But we would say the absolute pressure is 500 pascals plus the 101,000 pascals. So 500 pascals plus 101 kilopascals. In other words, 101,500 pascals. But the thing is, gauge pressure is enough for most purposes. We can describe the pressure at point 2 as the actual pressure, which would be 101,500 pascals, or we could describe pressure at location 2 as the gauge pressure, that is, how far above and beyond 1 atmosphere it is. Any questions on the meanings of those so far? And this is actually very similar to something else we've seen before. What's another measuring system we have for something else that we used back in 7A, where you can measure the absolute amount in terms of how far above actual zero, or you could measure just how far it is from some convenient reference point. Springs wasn't the example I was thinking of, but that's a good example where you could measure the actual length of the spring, or you could measure how far it is from the equilibrium. So that's another example of two different ways of measuring something, the absolute length or just how far it is from equilibrium. Also, do you remember what systems we were using for measuring temperature? What are the two different scales we usually use for measuring temperature? Yeah, Celsius and Kelvin. The difference between Celsius and Kelvin is very much the same idea as the difference between gauge pressure and absolute pressure. For pressure, we don't use different units of measurement. It's just pascals. But gauge pressure is very much like Celsius, and absolute pressure is very much like Kelvin. For example, if I say the temperature is 50 Kelvin, I'm saying it's 50 above absolute zero. 50 Kelvin is the actual temperature, how much temperature there is. Whereas if I say the temperature is 50 degrees Celsius, I'm just saying it's 50 above what reference point? What's the reference point that Celsius is measuring relative to? What's the zero? Yeah, 273 Kelvin. And what's important about that? Why do we use 273 Kelvin as the reference point? What conveniently measurable thing happens at 273 Kelvin or 0 Celsius? Yeah, freezing point of water. So that's very easy to measure and to know that something is at 0 degrees Celsius. So when we talk about the Celsius scale, Celsius is just measuring how far is something from the convenient reference point of the freezing point of water. If I say the temperature is 50 degrees Celsius, that just means 50 kelvins above the freezing point of water, a convenient reference point. Likewise, if I say the gauge pressure is 500 pascals, I'm just saying the pressure at this point is 500 pascals above and beyond atmospheric pressure, a convenient reference point. Also note that gauge pressure, like Celsius, can be negative. If I say the gauge pressure at this point is negative 40 pascals, what would gauge pressure being negative mean? Or let me get more specific. What would it mean if the gauge pressure is 0? Like if we're trying to measure the pressure and we find that the water doesn't rise up in the standpoint at all. So we'd have the 0 pascal mark. What would it mean if the gauge pressure is exactly 0? What does that tell you about the actual pressure at that point? Yeah, that means it is atmospheric pressure. This is one way of thinking about gauge pressure. Gauge pressure is a scale where we define atmospheric pressure to be 0. In gauge pressure, we define the atmospheric pressure to be 0 pascals and measure everything from there. That doesn't mean the atmosphere actually has no pressure. It just means that the atmosphere is the reference point we're using to measure everything else. So we're defining atmospheric pressure to be 0 if we're using gauge pressure. And any positive values tell you how much above and beyond that pressure the pressure is at the location we're considering. What would it mean for gauge pressure to be a negative value though? Like if we describe the location as having a gauge pressure of negative 50 pascals, what would that mean about that location? Yeah, the pressure at that location is less than atmospheric pressure. And that's entirely possible. Not in a situation like this, the water is going to be presumably higher than atmospheric pressure. But let's say you have a enclosed box and you attach a valve to it and suck some of the air out of it and then seal it off again. That interior of the box is now lower pressure than the atmosphere. Its absolute pressure would be less than 1,000 pascals. Its gauge pressure would be less than 0. In other words, a negative value. So gauge pressure can be negative. That just means that the pressure at that location is lower than atmospheric pressure, lower than the reference point. Whereas absolute pressure cannot be negative because absolute pressure being 0 genuinely means no pressure at that location at all. In the same way that you can't have negative Kelvin temperatures because 0 kelvins means genuinely no thermal energy. You can't have less than no thermal energy. Any other questions on that comparison, the idea of gauge pressure versus absolute pressure? And if we're talking about a delta, anytime you're looking at delta pressure, if you have pressure measured as gauge pressure and you want to convert to absolute pressure, you just have to add P atmosphere. But those are going to cancel out anyway if you're subtracting. So as long as you're talking about a delta pressure, you can use absolute pressure or gauge pressure as long as you're consistent about it. And I would generally recommend using gauge pressure when possible, simply because you don't have to worry about adding an extra 101 kilopascals to everything. Like if the water rises up in the standpipe 5 centimeters, you say that point at the bottom has a pressure of 500 pascals. You don't need to worry about adding 1 atmosphere if you're just going to be looking for a delta anyway. If you want the absolute pressure, if you just got pressure on its own without a delta attached to it, that should be measured as an absolute pressure. But if you're going to be just taking differences in pressure anyway, I would just recommend using gauge pressure for everything if possible. That way you can just measure how high does the water go in the column, multiply that by 100 pascals per centimeter or 10,000 pascals per meter, and then you've got the gauge pressure. Any other questions on that so far? So again, to recap, absolute pressure is the actual pressure at that location. Gauge pressure is just how different that pressure is from some reference point, typically atmospheric pressure. To convert back and forth, you would add or subtract one atmosphere, that is add or subtract 101 kilopascals. But if you're taking a delta pressure, the +1 atmosphere and +1 atmosphere cancel out when you subtract anyway. So you just get gauge pressure minus gauge pressure. Any other questions on that so far? All right, then let's try applying this to the actual praxis quiz. In this case, we are told that the water level in the 3 columns is always either 3 or 4 tick marks. And maybe the tick marks are centimeters, maybe not. But the important thing is we can effectively treat tick marks as a unit of pressure. Even though it's formally a unit of height, the whole idea of these pressure gauges is that each tick mark of height corresponds to a fixed amount of pressure difference, specifically the number of tick marks times density times gravity. So if we know that each column is going to show either 3 or 4 tick marks worth of pressure, as we go from 1 to 2 to 3, let's compare each of those individually. From 1 to 2, what should we expect is happening to pressure? Yeah, should be an increase in pressure. Exactly. From 1 to 2, the potential energy density is decreasing and nothing else is changing because we know this section has no resistance and no change in cross-sectional area and no pump. So the only other thing that can change is pressure. Decrease in potential energy density, nothing else going on means an increase in pressure. So we know location 1 is lower pressure and location 2 is going to be higher pressure relative to each other anyway. And then we go from 2 to 3. What's going on from 2 to 3? I wouldn't really say resistance increases. I would just say this section of pipe has resistance. Because keep in mind, resistance is not a property of the individual location. Resistance is a property of this section of pipe. There's no resistance at location 2, and there's no resistance at location 3. There is just resistance of the section of pipe from 2 to 3. That is, this section of pipe has resistance. And in that case, if that section of pipe has resistance, what would our Bernoulli equation look like? Yeah, we can ignore the other terms. We don't have any change in height, no change in cross-sectional area, so no change in speed. The only differences are going to be possibly a delta pressure, because you should generally include delta pressure to make up for other changes, unless you know for sure that the 2 points must be at the same pressure. No change in height, no change in area, no pump, but there is current flowing and there's resistance. So if there's current flowing in the direction from 2 to 3, what's happening to pressure? Yeah, we've got a decrease in pressure. The whole idea of the negative sign here attached to the IR, what that negative sign means is that there's a negative change in pressure. That is a decrease in pressure in the direction current is flowing. And it tells us the direction current's flowing here. Current is flowing from left to right. So since current's flowing from left to right, we should expect a decrease in pressure as we go from left to right, at least if the pipe has resistance. Or to put it another way, current flows in a pipe with resistance, current flows from the high energy density zone towards the low energy density zone. So we should expect 0.3 to have lower pressure, at least lower than 0.2. Doesn't relate to flow. Right, flow and resistance aren't really changing. Location 2 and 3 have the same flow rate as each other. And location 2 and 3 don't really have resistance. Resistance is a property of a section of pipe, not an individual point. Right, current is just a fixed value. Resistance is a fixed value for that section of pipe. But those multiplied together, along with this negative sign, tell you the overall change in pressure for that section of pipe. That's really what the negative IR term is all about. Negative IR isn't describing deltas in its own right. Negative IR is the process that's happening between those locations that influence how the total energy density is changing. In a way, you could treat the negative IR as being like the Q or W in the delta E total equals Q plus W equation. The left side of the equation is deltas comparing the two different locations or two different times in 7a. The right side of the equation is the processes happening in between that make those changes happen or influence those changes. Any other questions on that so far? And also, without more information, we wouldn't really know if 1 and 3 are the same low pressure. We just know we're going from some low pressure to some higher pressure to some lower pressure, but we wouldn't know how 1 and 3 compare. But part A specifically tells us that every one of these pressures, that is, every one of these columns, is giving either 3 or 4 tick marks. And since tick marks are a de facto measurement of pressure at the bottom, which ones would be 3 versus which ones would be 4? Yeah, 1 and 3 are 3 tick marks because they're lower pressure. And then 2 is the only one at a higher pressure, so that'll be the only one at 4 tick marks. So 3 tick marks of pressure, 4 tick marks of pressure, 3 tick marks of pressure. Any questions on that so far? And then in part B, we want to bring in some actual numbers, since it tells us the flow rate and it tells us the resistance. And we want to find what's the actual height difference between points 1 and 2. And this one may be kind of confusing at first because it gives us information about points 2 and 3, and then it's asking for information about points 1 and 2. But if we write out a separate Bernoulli equation for each one of those, like let's say we look at the Bernoulli equation from 1 to 2, what terms would we include in the Bernoulli equation from 1 to 2? Yeah, delta pressure, which we can even see from the difference in tick marks, plus potential energy density, rho g delta y. And since there's no resistance in this section, we wouldn't include any resistance. And of course, no pump either, and no change in cross-sectional area, so no change in speed. But what do we know about this delta pressure and this delta pressure from 1 to 2 and from 2 to 3? Yeah, they're the same, or at least the same magnitude. From 1 to 2, we're gaining 1 tick mark of pressure. From 2 to 3, we're losing 1 tick mark of pressure. So ultimately, what we need to do here is figure out what does 1 tick mark of pressure actually represent. And we can do that because it tells us values for I and R. If we multiply this current by this resistance, that current times that resistance should equal, at least as an absolute value, should equal 1 tick mark worth of pressure difference. Then we could fill in that 1 tick mark worth of pressure difference written in terms of pascals and solve for delta y in terms of meters. Any questions on that? So for instance, if we fill that in here, we've got -3 cubic meters per second times 2000 joule seconds per meter to the sixth. Multiply those together and what do you get? Yeah, negative 6,000. And the units reduced to joules over meters cubed, which is the same as pascals. So that means one, and that represented one tick mark. We know that the change in pressure from B to C was -1 tick mark. -1 tick mark. So -1 tick mark is negative 6,000 pascals. In other words, one tick mark means 6,000 pascals. We now have a conversion factor for tick marks of pressure versus actual pascals of pressure. We can now fill that in the Bernoulli equation from 1 to 2. We know delta pressure is also one tick mark, so we can write that as 6,000 pascals. And then density and gravity are the usual 1,000 for water and about 10 for Earth's gravity. And delta Y is the only unknown left. So at that point, you can now solve that for delta Y and get something like what, 0.6, I think? Yeah, it should be about 0.6 meters. So that means from 1 to 2, there's a height drop of 0.6 meters. Any questions on that? Or any other questions about this quiz or more generally standpipes or pressure? Oh, that's right. There's another part to this, isn't there? So in this case, it looks like we've got the same sections of pipe. But we're doing something a little differently. In this case, water's flowing to the left. Oh, and also we now we now have resistance in the section from 1 to 2. And C still has 4 tick marks of pressure. So if we still have 4 tick marks of pressure for C, and we want to figure out what happens when we go from C to B and from B to A. However, we're keeping the same amount of resistance. From 3 to 2 is still the same resistance as from 2 to 3. We're just reversing the direction of current. If current flows, the same amount of current flows through the same pipe resistance, what's going to happen to pressure from 3 to 2? If you got current flowing through a pipe with resistance, what would you expect to happen to pressure? Yeah, we should expect a pressure decrease. And if you're not sure, you could always write out the Bernoulli equation. In this case, you just have delta P equals negative IR because nothing else is changing. The negative sign signifies that in the direction current is flowing, there's a decrease in total energy density. So we should expect 0.2 to have lower energy density than 0.3. And the only one that's changing is pressure. So we should expect lower pressure. And specifically, how much lower? How many tick marks does that current times that resistance correspond to? Right. It's still one tick mark of difference. It's just a difference in the opposite direction. Now 3 is high pressure and 2 is low pressure. So that means from 3 to 2, we've got a decrease. The absolute value of that change is still 1 tick mark worth of difference. So we're going to drop from 4 tick marks to 3 tick marks. And then we're going from 2 to 1. From 2 to 1, what's changing? Yeah, we now have resistance. And it's the same resistance as the resistance between 3 and 2. So we're going to have a negative IR term. And specifically, how much pressure would be losing due to the IR? If we've got the same current, yeah, same current and same resistance, so it's still going to multiply to losing 1 tick mark of pressure. But that's not the only difference here. What else is changing from 2 to 1? Yeah, we've also got a height increase. So we need to account for potential energy density. And specifically, if height is increasing, what would we expect to happen to pressure? Yeah, height is increasing. That's a gain in potential energy density. So we should expect a loss in pressure. And specifically, how much pressure? What's the change in pressure associated with that difference between 1 and 2? We saw this back in part 1A. Yeah, that was also 1 tick mark worth of difference. Based on what we saw in part 1A, there's a 1 tick mark difference between 1 and 2 due to height. So from 2 to 1, we're losing 1 tick mark of pressure associated with the height increase, but we're now also losing 1 more tick mark of pressure related to the dissipation increase. So what should be the final pressure at location 1? If we combine these losses? Yeah, we had 3 tick marks, we lose 2 tick marks of pressure, we're now down to just 1 tick mark of pressure. So final pressure at location 1 should just be 1 tick mark of pressure. And keep in mind, these are all gauge pressures. If we want absolute pressures, we'd convert 4 tick marks to pascals and add 101. Convert 3 tick marks to pascals, add 101. Convert 1 tick mark to pascals, add 101. But I think gauge pressure should work fine here because ultimately what we care about is how high the water rises in the column anyway. And that's all about gauge pressure. Any other questions on that? You're welcome. See you next time.